So in this video, I'm going to talk about how much energy you need to put an object into orbit, and then we'll talk about if it is already in orbit, what it's going to take to get it the rest of the way away from the Earth. So, just to give us some numbers to work with, let's make our satellite 1500 kilograms. Let's make the period of the stable orbit that we want 12 hours. So it's going to set this object will circle the Earth twice a day, and we'll figure out how much energy it would take to get that object into that orbit, and then we'll figure out how much more energy it would need to just get away from the Earth completely at that point. So the first thing I need to do, actually I can't start with energy, I have to start with forces, is I have to figure out what the distance from the center of the Earth that stable orbit would have. It's a period of 12 hours. So in 1 hour I have 3,600 seconds. So if I'm going to go 12 times 3,600, 43,200 seconds in that 12-hour period. So with that in hand, I'm going to want my gravitational force between the Earth and the satellite to be what's causing the circular motion. And I don't want to use this formula, I want to use 4 pi squared r over t squared because I have the radius, or I have the period, I'm looking for the radius. And then you'll notice the mass of the satellite is on the other side. The mass of the satellite can't be zero, or it's not zero, so we can go ahead and divide it out. And now we can get an expression for the radius associated with this stable orbit, GME period squared, bringing the 4 pi squared down here. The two radiuses up with the other radius to get radius cubed, and then cube rooting both of these guys. Now, we kind of know from previous examples or just from a data sheet that the mass of the Earth is 5.98 times 10 to the 24 kilograms. So we could go ahead and stick all our values in here now. And it's big and it's ugly, but it's just a formula, so we can plug it into our calculator. 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared times the mass of the Earth, 5.98 times 10 to the 24. That'll be kilograms. Times the period, which will be, 43,200 seconds squared. And that'll all be divided by 4 pi squared. Okay, and that's all going to be a radius. So 6.67 exponent negative 11 times 5.98 exponent 24 times 43200 squared divided by 4 divided by 3.14 squared equals, and then cube root that, and I got a radius of 2.66 times 10 to the 7 meters. I've just been doing this, so it'll be kind of interesting to look at what happens with the units in here. So I have Newton meter squared per kilogram squared. I've got the mass of the Earth at kilograms, and then when I square those seconds, I'll have seconds squared. So one of the kilograms will cancel that kilogram, and then remember that a Newton is equal to a kilogram meter per second squared. So we'll have Newton kilogram meter per second squared times meter squared divided by kilograms times seconds squared, and the seconds cancel the seconds and the kilograms cancel the kilograms, and we're left with meters cubed. Then we cube root it, and that's how we get back to meters. Anyway, so that's the radius associated with the stable orbit that has a period of 12 hours. Once I have that, getting the energies is pretty straightforward. I'm going to start by finding the gravitational potential energy, G m1, or mass of the Earth, mass of the satellite, divided by the radius of the satellite, and make that negative. And so I can put all my values in here, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, mass of the Earth 5.98 times 10 to the 24 kilograms. Mass of the satellite, I think I made it 1,500. Yeah, 1,500 kilograms. Divided by the radius of the orbit, which is 2.66 times 10 to the 7 meters. So I'll just plug all this guy in here. 6.67 exponent negative 11 times 5.98 exponent 24 times 1,500 divided by 2.66.7. So the gravitational potential energy, just to be clear, this is in orbit, is negative 2.25 times 10 to the 10 joules. Okay, now with this in hand, I'm going to go and find a few different things. First of all, I want to know the total energy in orbit, or I could call it the binding energy. And we can recall, if you want to go back and watch a previous video, that the binding energy is equal to 1/2 of the gravitational energy. So this is no trick. I can just divide this guy by 2, and I'll get 1.125 times 10 to the 10 joules of energy as my total energy in orbit. To get this thing into orbit, I have to remember that it started on the surface of the Earth. Now, we're going to have gravitational potential energy on the surface of the Earth, but we're not going to have kinetic energy. It's not to say that the object wasn't moving, but it's not moving at a pace that's fast enough to generate enough energy to be interesting. So maybe, the rotation of the Earth is having this thing move at some sort of speed, but it's so slow in comparison to the amount of energies, the size of energies that we're looking at here, that the kinetic energy of this object on the surface is basically ignorable. The kinetic energy in orbit was not ignorable, but that's because this thing's going so fast that it can maintain a stable orbit. But when it's sitting on the surface of the Earth, it might be moving, but it's not moving very fast, so we're just going to ignore that. Even though it's on the surface of the Earth, because it's coming all the way off, we still have to use the universal gravitational formula for energy. So to get its energy, and this will be its total energy, I'm just going to do the potential energy calculation. Meters per kilogram squared. Mass of the Earth is 5.98 times 10 to the 24 kilograms. Mass of the satellite is 1,500 kilograms. And this is all going to be divided by the radius. And in this case, we're going to use the radius of the Earth, which is 6.37 times 10 to the 6 meters. That's an average value. So 6.67 exponent negative 11 times 5.98 exponent 24 times 1,500 divided by 6.37 exponent 6. And I get 9.4 times 10 to the 10 negative joules. I'm just going to do that one more time. Yep, that looks right. Okay. So on the surface is our energy 1 situation. In orbit is where we want to put this thing, so that's our E2. So to get our work, we look at the difference between E2 and E1. You might look at this and say this looks bigger, but remember it's negative. So if we imagine this graph, we're starting somewhere down here associated with the orbit of the Earth, and we're trying to come up to somewhere here in a stable orbit. So we have to put energy in to increase that. That's the change in gravitational energy. Keep in mind we also need to add kinetic energy to get up to a stable orbit. So this is a bigger number than that, but they're both negative. So it's still an increase in energy to come up to it. mathematically we can see that we are subtracting away a negative, and so it's going to turn into a positive energy. That's a 9.4, not a 9.1. So I need to put in 8.275 times 10 to the 10 joules of energy to get it from the surface of the Earth to this stable orbit. That's the work that needs to be done. Part B of this question, I'm just going to attach to my thing here so I don't run out of batteries. There we go. Part B here says how much energy to get completely free. And if we remember our definition for binding energy, since this is the total energy and I want to go to a zero energy state, then this is how much energy I'm going to have to provide. So now we're going to assume that energy 1 is our energy with the stable orbit, negative 1.125 times 10 to the 10 joules of energy, and we're going to want to go to an E2 state where we actually get back to zero energy. So the work we're going to have to put in this case, E2 minus E1, is going to be equal to 0 minus the negative 1.125 times 10 to the 10 joules. Or we're going to have to repay that deficit of energy that we still have to get back completely out of the gravitational potential well and get back to a zero energy situation. So that is how much energy it takes to get away from the planet, how much energy it takes to go into orbit, all for, 1,500 kilogram at a 12-hour period. I don't know, I just sort of chose those arbitrarily. So those are the energies, a specific example for a stable orbit.